let's talk about similarity in right triangles. First thing we got to know is, what is the geometric mean? The geometric mean of two positive numbers, okay, it's always positive. Geometric mean always positive. The two numbers a and b is the positive number such that if I set up the proportion with x being the geometric mean and take the cross product, then I'll get x squared. If I did this cross product right here, I'd get x squared equals a times b, right? And then if I solved it, I'd get x equals the square root of a times b. And you remember from Algebra 1 that typically when we solve an equation by taking the square root, we would want to put a plus or minus there, right? But why don't we do that? Because we said that the geometric mean is always positive. That's why we don't need plus or minus. So the geometric mean, anytime I ask you to find the geometric mean of two numbers, you're just going to set up a proportion. So if I want the geometric mean of 4 and 7, I'm always going to make the mean my means. Maybe that'll help you remember it. Make the mean your means. All right, and then I put my two numbers as the extremes, and then I just cross multiply. So I get x squared is 28, and then I've got to say that, okay, then x is the square root of 28, and then I need to simplify that radical. What is that? Well, the perfect square in 28 is 4. Square root of 4 is 2, so the geometric mean of 4 and 7 is 2 times the square root of 7. Okay, what if I want to know this? 6 is the geometric mean of 12 and what number? Okay, well I know what the geometric mean is, right? I told you, so I'm going to put it here as the means. 6 is the geometric mean of 12 and what number? Just take the cross product. 12x is 36, therefore x has to be 3. So 6 is the geometric mean of 12 and 3. Okay, now here we go. We got to know this when we start talking about similarity in right triangles. So here's a theorem. Doesn't have a name. It says the altitude to the hypotenuse of a right triangle. So let me just, I have a picture here, but it's kind of blurry. So let me just try to draw one over here that might be easier for you to follow. And I'll fill it in as I'm reading. Okay, so here we go. Right triangle. So the altitude to the hypotenuse. So this would be right here. This would be the altitude to the hypotenuse of a right triangle. This is our right triangle here that I drew in green. Divides the triangle into two triangles that are similar to the original triangle and to each other. Okay, so if I call this A, C, D, B. So what happens when I drop this altitude, this blue right here, this altitude, by definition the altitude is perpendicular to the base, right? So I make myself two more right triangles. So now altogether I've got 3 right triangles, and all this theorem tells us is that all 3 of those right triangles are similar. Okay? So there we go. All 3 of those right triangles are similar. Okay, now for the corollaries. The first corollary, pretty straightforward. The second one, this is going to be the one that haunts you. But let's do the easy one first. Okay, so the length of the altitude to the hypotenuse of a right triangle, so that's this one right here, CD. So in this picture, the length of the altitude to the hypotenuse is the geometric mean of the lengths of the segments of the hypotenuse. Okay, what does this mean? The segments of the hypotenuse. I'm going to draw them in green. So you see this altitude, the blue, that I dropped from the right angle to the hypotenuse, it divided that hypotenuse into 2 segments, right? I just highlighted them in green, okay? And what this is saying is that the geometric mean, which is in blue, this altitude, which is blue, is the geometric mean of the lengths of the segments that it divided that hypotenuse into. Okay, so just let that sink in for a minute. When I drop this altitude, CD, it's going to be the geometric mean of the two parts that it divides the hypotenuse into. Okay? Now, corollary number 2. This is the one you're going to have to spend some time with in order to keep it straight. I'm going to read the words, and the words probably not going to mean a lot to you. The altitude to the hypotenuse of a right triangle separates the hypotenuse so that the length of each leg of the triangle, so when I say the length of each leg of the triangle, I'm talking about these two, AC and BC. The length of each leg of the triangle is the geometric mean of the total length of the hypotenuse and the length of the segment of the hypotenuse adjacent to the leg. Whew, I know that's a lot. Here's what it means. Okay, so the length of each leg. Okay, let's start with CB, right? Is the geometric mean. CB, the length of each leg is the geometric mean. So CB, so I put CB here, because that's the geometric mean. That's what this corollary is telling me. But what is it the geometric mean of? It's the geometric mean of the complete hypotenuse, the length of the hypotenuse, which is AB, and the length of the segment of the hypotenuse that's adjacent to that leg. So here's the piece of this hypotenuse that's adjacent to that leg. Okay, so down here, I gotta have DB. That's all that corollary says. Okay, so let's look at AC. AC is the other leg, right? Here's the other leg. The other leg, AC. Okay, so AC is the geometric mean. Remember, I always put my geometric mean as the means. Okay, what is it the geometric mean of? It's the geometric mean of the complete hypotenuse, AB, and the segment of the hypotenuse that is adjacent to that leg. So that would be this part, right? That's the segment that's adjacent to this leg. So what do we got to put down here? AD. AD. There you go. That's it. Now, we got to do a lot of problems so you understand how to use that and don't forget it. So here we go. You know, I'll probably do some and then I'll ask you to do some on your own. Okay, this is the theorem, right? This is the theorem. I'm trying to find the altitude. Well, I know the altitude is the geometric mean of the two segments that it divides the hypotenuse into. So it's divided into an 8-inch or 8 units and a 4 units. So I simply got to put my 8 and 4 there. I get x squared is 32. X is the square root of 32. Therefore, x is going to be, that's 16 times 2, so 4 times the square root of 2. So that's how long that altitude is. Okay, how about this one? Okay, this is going to be the corollary, right? Because we got one of the legs. We got one of the legs. So let's do the leg corollary. So I know that I know that leg is the geometric mean. Always write that first. And what is it the geometric mean of according to the corollary? The total hypotenuse length. So that's 8. And the segment of the hypotenuse that's adjacent to that leg, which is 2. Okay. So what do I have when I do my cross product? Y squared is 16. Therefore, y equals 4. So the length of that leg is 4. Could I find the length of this leg? What if I wanted to find the length of this leg? I could. Well, I could use the Pythagorean theorem, but let's say I don't want to do that. I want to do it by proportions. Let's call this leg x. What do I know about it? I know that it's the geometric mean of the total hypotenuse and the segment of the hypotenuse that's adjacent to it. Okay, so that gives me x squared is 48. Therefore, x is going to be the square root of 48, which will be 4 times the square root of 3. So I can get all my side lengths there. Could I figure out what the height of this altitude is, or the length of this altitude is? Of course I could. If you want to, go for it. All right, let's see what we got here. Okay, the altitude is the geometric mean of the two segments of the hypotenuse. So t squared equals 17 squared, so t equals 17. I'm not going to do 17 squared and then take the square root of it. That would be silly. Okay, why don't you do this next one and then come back and check it? Did you get z equals 3 times the square root of 10? I hope so. What do I know? I know that z is the geometric mean of the total hypotenuse, which is 18, and the segment of the hypotenuse that's adjacent to z, which is 5. Take the cross product, z squared is 90, simplify the square root of 90, you get 3 times the square root of 10. All right, you got 1, 2, 3, 4 more problems here. I want you to do those, come back and check. Please check your answers here. Let me know when you come to class if you have any questions on these. All right, one more problem of the day. We like to interject some real life. So what do we got here? We got an architect's drawing of a little house, and it shows a post here. Here's our little support post, and I can see that that's a geometric mean. All right, the support post is 10 feet tall. I'm going to go ahead and fill that in here. You may find yourself looking at some architecture drawings one day, or hey, you may be drawing them. So geometry, good stuff to know. So the support beam is 10 feet tall. And what do I know? I know this whole line here is 25 feet. That's 25 feet. So what I want to know is how far from the front of the house. So here's the front. You see it's labeled front right here. So this is what I'm trying to figure out right there. That little distance from here to here. How far is that post from the front of the house? So, well, what did we say we know? We know that that post length is the geometric mean of what the two segments, this side over here, this long side that I drew in blue, it's the hypotenuse. It's the hypotenuse. It's 25, but I need the two parts, the two segments. So if I know the total hypotenuse length is x, 25, and I'm calling one part of it x, this right here, this is going to have to be 25 minus x, right? So let me put that down here. Okay, let's take the cross product. So I'll get x times 25 minus x equals 100. Negative x squared plus 25x equals 100. So looks like I'm gonna have to factor this. I don't want this negative x over here, so I'm gonna take everything to the right side. Set this side equal to 0. X squared minus 25x plus 100. Now I got a factor. So 0, let's see, I need the factors of positive 100 that add to negative 25. So I'm thinking of negative 20 and negative 5. Right? I think that does it. X squared minus 25. Yeah, that'll do it. So when I set each one of these equal to 0, I get x equals 20 or x equals 5. Well, in this case, it can't be both. It can't be both, but I can tell from my engineer drawing that x is 5 because this part right here is definitely shorter than this part over here, so I know that this part is 5 and this part over here is 20. So even though I got two legitimate solutions, there's only one realistically that works for me here, and is that that support post is 5 feet from the front of the house. We have one more lesson left in this unit. It's proportions in triangles. We'll see you then.